What's f of -1?
Ax plus 5.
So it's the ax plus 5 part, but if we're evaluating it at -1, we got to plug in that -1 for x, right? So that'll give us -a plus 5. Everybody good with that being f of -1?
Yep.
Yeah.
Okay. Now the second part of this said what? Said that the limit needed to exist. So the limit as x approaches -1 of f of x. Well, if I'm looking for the limit as we approach -1, do I use the value at -1? Or do I use what's happening as we get close to -1?
As you get close to negative.
As you get close.
Right, so we got to take x cubed plus 3x squared plus 3x plus 1 over x plus 1, which unfortunately, when you plug in -1 to that, is 0 over 0. It's indeterminate. So how do we deal with an indeterminate limit? Hopefully by doing some factoring. What's that numerator factor to?
Would it be x plus 1 cubed?
It would be exactly that. And so now we can turn this into a limit as x approaches -1 of just x plus 1 squared if we cancel out one of the x plus 1s in the numerator with the one in the denominator. And what does that limit come out to be?
0.
0, exactly. It comes out to be 0. So criteria 1 has been met, criteria 2 has been met, right? F of -1 exists, and the limit as x approaches -1 exists. Criteria 3 says the first one, -a plus 5, needs to equal the second one. And that just gives us a equals what?
5.
Exactly. So if a is 5, that fills in the gap. That makes this function continuous for all real numbers. It makes it continuous at -1, and we already knew that it was continuous everywhere but -1. Good or no?
Good.
All right, awesome. But before we can talk more about limits, what we're going to do is we're going to go way, way back to when you were in like first grade and first learned about slope, right? And what slope is. Slope, or sometimes called the average rate of change, the slope is just how much change we have in our function by how much time it takes to make that change, right? It's a change in the y divided by a change in the x, right? Delta y over delta x, or y2 minus y1 over x2 minus x1, right? That's slope, right? You're all familiar with slope, right? You might have called it rise over run, right? y2 minus y1, x2 minus x1, delta y over delta x, change in y over change in x, all these different things. These all mean slope, right? An average rate of change is just a fancier way of saying slope. And the only reason I bring up average rate of change, well, not the only reason, but one of the reasons I bring it up is because sometimes on the AP test, they will ask you this first grade question, like this one, of what's the average rate of change of a function on this interval? And all they want to know is the slope. And the reason they're asking you that is because they're trying to confuse you between a bunch of other things that we call like the average value formulas or the mean value theorems. There's a couple of different mean value theorems or average value formulas, and they're just trying to confuse you. But slope is very, very, very important towards all of what we're going to do with calculus for the rest of this year. So before we can do any of that, I want to make sure you can find me a slope. So find me this slope of f of x equals x cubed minus x over the interval -1 to 3. How would we do that? We'd find f of 3 and subtract f of -1 and divide it by 3 minus -1. Would you all agree with that? That's how you find the slope.
Yes.
Good. All right. What's f of 3? 27 minus 3, so 24. And minus f of negative 1, which is negative 1 plus 1, which is 0. And then a 4 down there, 6. Okay. Should be very easy to find the average rate of change. What if I wanted you to find the average rate of change between negative 1 and 4 for this function? Could you do it? I'm not asking you to do it. I'm just asking if you could do it. Could you do that?
Yeah.
Oh, somebody is still there. You could. You could find that slope between negative 1 and 4. Would you be annoyed that you had to do it? Because it was so easy?
Probably.
Probably, yeah. And then if I said, all right, find the slope now of this function between 2 and 5. And then I said, all right, actually, here's 20 different sets of points on this function. I want you to find the slope between negative 1 and 3, and then negative 1 and 4, and then 2 and 5, and then 0 and 7, and then negative 3.8 to 2.7, and then 16 to 18.2, and then from e to pi, and then from pi to 7.2, and so on and so on and so on. Would you be really annoyed that I asked you to do that?
Wouldn't the slope just be the same?
Not necessarily, because this is not a linear function. Right? If it's a linear function, the slope doesn't change, but the slope changes a great deal on anything that is not linear. Right? And it shouldn't come out to be the same for probably any of those. Conceptually, could we do that? Could we go in and find those slopes?
Yeah.
Yeah. How annoying would that be?
Very.
Very annoying. That's the answer I was looking for. How much less annoying would that be if I gave you a formula that you could just use for the slope between any 2 points, where you didn't have to like calculate f of 17 and f of 19.2 and then do all of the actual arithmetic? Wouldn't it be easier if I gave you an actual formula, a generic formula for this particular function?
Yeah.
Yeah, that'd be nice, huh? Well, we're going to learn how to develop that generic formula for a function, not necessarily this specific function, but for any function right now. So here's what we're going to do. We're going to take a plain, boring, simple little function here. We'll just call this function f of x. Okay? And we're going to write a formula for the slope between these 2 points. For the slope, we call it a secant line, a line that touches in 2 different points, right? Secant line through those 2 points. We want that slope. Okay? And we're going to use the points x f of x and x plus h f of x plus h. So if this is x and this is x plus h, what is this?
H.
H, right? All right, so how would I write that slope? I would use the slope formula. F of x plus h, right? Minus f of x, wouldn't that be the change in y values? All over the change in x values, which would be x plus h minus x. And with any luck, we could simplify the denominator of that down to give us f of x plus h minus f of x all over h. Does that look familiar? Is that something you guys have all seen before? This formula right here? No. This is called the difference quotient. The difference quotient is just a generic slope formula for any function. F of x plus h minus f of x over h. Everybody good with how we came up with that formula?
Yep.
All right. Hopefully so. There's a lot of you that are very quiet out there, so I'm hoping you're all paying attention and this is making sense, because this is really going to matter as we go forward. So this, if I were to evaluate it for, let's say, my function x cubed minus x, I would just plug in x plus h for x, and then subtract the function and divide by h. And that should give me a formula that would give me the slope of that function at any point. So let's see if we can do this. We're going to do this for this particular function, x cubed plus 2x minus 1. We're going to see if we can find the slope of the line that goes through any 2 points on that graph using the difference quotient, f of x plus h minus f of x all over h. So what's f of x plus h? Okay, let's try it. What is f of a?
A cubed plus 2a minus 1.
Right, a cubed plus 2a minus 1. What's f of, I don't know, z? Z cubed plus 2z minus 1, right? So what's f of x plus h? X plus h cubed plus 2 times x plus h minus 1. Do you guys agree with that? Plug in the x plus h.
Yes.
Yeah.
Okay, then we're going to subtract our function and divide by h. All right, let's simplify this out. How can we simplify out x plus h cubed? That's just the binomial theorem expansion, right? We should all know that using Pascal's triangle. Distribute out the plus 2x plus 2h. Oops. Minus a 1, minus an x cubed, minus a 2x, and plus a 1, if we distribute the minus sign through everything. All over h. Good or no?
Yeah.
Yeah, how much simpler does this seem now? So much simpler, right? Probably not really. What we'll note though is that any of these terms that I can cancel, I will, and any of the terms that don't have an h in them will all cancel. So x cubed and minus x cubed, 2x and minus 2x, minus 1 and plus 1 should all cancel out. And we'll only be left with a bunch of terms in them that have an h. And then I'll be dividing it all by h, which will allow me to just cancel out 1h from every term in the numerator. And we'll end up with 3x squared plus 3xh plus h squared plus 2. This little formula that we've written here, this tells us the slope of a line that goes through any 2 points of this particular function, only this particular function. So let's real quickly open up Desmos. And what do we have? We have x cubed plus 2x minus 1. Is that what we had?
Yeah.
Okay. Let's see if we can find the slope of the line that goes through the point at x equals 0 and through the point at x equals 1. So that's the point 1, 2, and the point 0, negative 1.
Oh wait, I think it was plus 1. Oh no, never mind. Sorry.
Okay. So we're going to find the slope between x equals 0 and x equals 1. So first off, if we think back to our picture that we had drawn back here, the x value that we start at for our particular problem now is 0, right? And the x plus h, remember the h is the distance between them. So the distance between 0 and 1 is 1. So we got x equals 0 with h equal to 1. Everybody good with that? So let's plug in x equals 0, 3 times 0 squared, plus 3 times 0 times 1, plus 1 squared, plus 2. What does that give us?
3.
Gives us 3, which tells us that the slope between x equals 0 and x equals 1 of this function is 3. How would we write the equation of the line if we wanted to? We don't need to, but how would we write the equation of this line? If we know the y-intercept, or if the y-intercept was what? 0, -1. So what would the equation of the line be? Y equals mx plus b. Y equals 3x minus 1. So if we go in here and take a look at that graph and draw this graph of 3x minus 1, we'll see that it goes through the point at 0, -1, and it goes through the point at 1, 2. And the slope between those 2 points was clearly 3 because it went through those 2 points. Suppose we had, instead of doing, let's say, 0 to 1, let's say we had done -1 to 1. So we'll real quickly go back here. Suppose we were doing -1 to 1. And we had 3x squared plus 3xh plus h squared plus 2. And we wanted to go from x equals -1 to x equals 1. Well, what would the h value then be?
2.
2. Okay, so plug in x equals -1 and h equals 2 into that formula and let me know what you get as your slope. Did I do my arithmetic right? Should it be 3 again? You guys agree with 3? Okay. And let's see, if I were to try and write the equation of that, it needed to go through the point -1, comma, what was the point on the graph at -1? -1, it was -4, right? So if it's going to go through that same point, it's probably going to have that same equation. It needs to go through -1, -4. So that'd be y minus -4 using point slope form equals 3 times x plus 1. And if we were to simplify that down, we'd get y equals 3x minus 1. And we'd see that, yeah, that same line cuts through -1, -4, and through the 1, 2 point, and it still has a slope of 3. All right, we're going to do one more set of points here. Let's do x equals, let's do x equals 1 to x equals 2, so we can get a different line. So we're going to go from x equals 1 to x equals 2, which tells us that what's the h value?
1.
1. So we had the formula, what was it, 3x squared? What was it, 3x squared plus 3xh plus h squared plus 2? And if I plug in x equals 1 and h equals 1, that becomes 3 plus 1 plus 2. Gives us a slope of 9 this time. And if we're going through the point at 1, the point at 1 was what, 1 comma 2, is that right? Which ought to be y minus 2 equals 9 times x minus 1. And we should see that if we go plug this in, y minus 2 equals 9 times x minus 1. It should go through the point at 1, 2, and it should go, should go through the point at 1, 2, and it should go through the point at 2, 11, and it should connect those 2 points with a straight line, right? It gave us that slope of 9 between those 2 points. Everybody good with that? That's what this is doing. That's a very important concept. It may not seem like it yet, but it is. Good or no? Good. All right, cool. Let's do a different function. We're just going to do one more of these. This will be the last one of these that we do for now. And see if we can write an equation. We're not going to plug in all the points this time for it, but see if we can write an equation to find the slope of the line that goes through any 2 points of this one, 1 over x squared. So first off, we need to find out what f of x plus h is, right? What's f of x plus h? Should be just that, right? And what about f of x is just that, all over h. How do we simplify this complex fraction? How do we simplify a complex fraction?
Common denominator.
Common denominator. So we're going to put in an x squared and an x squared, and we'll put in an x plus h squared and an x plus h squared, which is going to give us x squared minus x plus h squared, which is x squared plus 2xh plus h squared, all over, we have an x squared and an x plus h squared, and then that h, which is really like an h over 1, gets multiplied in with that same denominator. So x squared h, x plus h squared. Good or no?
Good.
Or distribute the minus sign through and the x squareds cancel, and you're left with negative 2xh minus h squared over x squared h times x plus h squared. And what happens again? Everything in the numerator that had no h's in it canceled. So I'm left with all terms with h's, and I can cancel that with the h in my denominator. And we get this, that formula right there. And that's the formula for this particular function. That would give me the slope between any 2 points on the graph. Easy enough?
Yeah.
All right. Now you're probably sitting there thinking a couple different things. One, this is boring. One, I'm sick of doing this. Sorry, 2, I'm sick of doing this. And 3, why the heck does any of this actually matter? Well, finding the slope of the line through any 2 points doesn't really matter all that much. But what we really want to concern ourselves is what is happening at one specific point. How much is our function changing right at one point, any point that we might choose? At some instant in time, we'll say, if we're talking about, x is like a time variable sort of. At some x value, some time x, how much is our function changing at that instant? We call that the instantaneous rate of change. And that's what we want to really concern ourselves with. But that's not what we have here, right? We have, for both of these things that we just did, we have this interval from x to x plus h. Right? We have this secant line. We have this long interval. It might be between 1 and 2, or it might be between 1 and 100, where we're finding the slope. Well, if we really want to concern ourselves with what's happening at an instant, at just, let's say, just at x, what do I need to do with h?
Make it 0.
Make it smaller and smaller and smaller until it is 0. That's exactly what we want to do. So we want to try to shrink down this interval of h all the way down to 0 and look for the average rate of change then. So before we try to do that, let's think about this. F of x plus h minus f of x over h, right? Well, if I want h to be 0, isn't that a bit of a problem? Like right off the bat. If I want h to be 0, why is that a problem?
It would become undefined.
Yeah, I mean, there's a division by h, which is a division by 0. And not only that, if you look at the top, if you plug in 0, plug in 0 for h into the top is also equal to 0. We'd end up with this indeterminate thing that we've dealt with limits before, but not without a limit in front of it. So that's a problem. But it's a problem that's easily solved by, instead of saying what happens at 0, we will look at what happens as we get very, very, very close to that interval being 0. So if I get very, very, very close to that interval being 0, that'd be a limit as that interval gets very close to 0, right? H approaches 0 of f of x plus h minus f of x over h, which is still indeterminate. It's still 0 over 0, but once it's a limit, there are lots of different ways that we can deal with that. All right, we can factor, we can multiply by conjugates, we can do the complex fraction thing, we do all this other math to help us to evaluate this limit. Okay? And this limit right here does one thing that has a lot of different names. One, it's called the derivative. This is the limit definition. That's supposed to be a v of the derivative, but that derivative tells us the slope of the tangent line to a function. It also tells us, this is one thing that it's called. It's also called finding the slope of the function at a specific point. And it's also the instantaneous rate of change. Okay. And the question sort of becomes, why does this work, right? And we've been doing it with a secant line, right? Well, what we're effectively doing is we're making the interval for our secant line, for this line that goes through 2 points, very, very, very small. And so I want to take a look at, back to this x cubed plus 2x minus 1 function, okay? And we're going to pick a point and zoom in and get a very small interval. So if you look at this curve, you all can see the curve right now, right? X cubed plus 2x minus 1. You all can see, yeah, okay. If you look at it right now, it definitely looks like a cubic function, right? It looks like a curve, doesn't it?
Yeah.
Yeah, let's look what happens when it zooms in. We're just going to zoom in a little bit at a time. Does it still look like a curve? Sort of like a cubic? A little bit, right? A little bit less, but it's still got that curving to it. What about now?
A lot less.
A lot less. What about now?
It just looks linear.
Yeah, it almost looks linear now, right? And I'm not even on that small of an interval, right? And these are all, each one of these is 0.05 right now, which is small, but not that small. And the more and more I zoom in, the less and less it begins to look like a curve, and the more and more it begins to look like just a straight line. We call that idea linearization, right? This is called linearization. And it's the idea that if I zoom in really, really close on any point, I chose at x equals 0 here, right? X equals 0, y equals -1. Could have been any point though. I chose any point to zoom in on, it begins to look like a straight line. And so if I take the interval of h and make it very, very, very small, well, that line that goes between 2 points of this on this tiny interval is almost exactly the same as the function is on that very, very tiny interval. You guys see that how that would sort of work, that the function begins to resemble this line that's right next to it. If I were to draw a line through there between, like, let's say this point and this point, Do you think you'd be able to see much of a difference between the cubic and the actual linear function if I were to draw that line?
No.
Probably not, right? So that's the whole point of this. Looks like a cubic, zoom it in, and it looks like a straight line. Doesn't matter what function you choose. Pick some function like x squared. Well, it matters for some functions, but let's look at x squared. It sure looks like x squared is a parabola, right? Do you agree?
Yeah.
Sure looks like one. That's because it is one. Let me zoom in. Does it still look like a parabola?
Yep.
Yep. How about now? Still look like a parabola to you?
No.
Not really.
No.
Nope, not really. It looks like just a straight line there, right? Because we've zoomed in so far. We know it's still a parabola, but even at one of these places where it's like turned from going down to going up, if I zoom in enough, it just looks like a straight line. And the line that goes through any 2 points of this would be almost exactly the same as the function. So if we can find the slope between, 0 to 0.00002, that should be close enough to the actual slope of the function at 0. Good or no?
Good.
All right, so here's what we're going to try to do. We're going to see if we can find the equation of the line tangent to f of x equals x squared plus x. And I did this last period with x equals 3, and I didn't really like it with x equals 2. So we're just going to do this with a real simple one. We're going to do this at x equals 0. And I think that's going to help us to illustrate this point a little bit better. So if I want to find the equation of the tangent line, that's one of these things that I said this was, right? The slope of the tangent line can be found by using this. And so if I want to write the equation of a line, the tangent line to it, then I need to find the slope first, right? I need a slope and I need a point, don't I? To write the equation of a line.
Yes.
Yeah. So first off, what's the point? The point ought to just be 0, comma f of 0. And that would be 0, 0. Point was an easy one to find, right? Now we need to find the slope of the function, or the slope of the tangent line to this function at x equals 0. So we're going to go through and use this difference quotient and find this limit as h approaches 0 of x plus h squared minus, plus x plus h. That's my f of x plus h squared plus x plus h, minus x squared plus x, all over h. And this, right, m equals, that's our slope. Okay. We'll expand everything out. X squared plus 2xh plus h squared plus x plus h minus x squared minus x all over h. And just like all the ones before it, any term that didn't have an h in it cancels out. And we're just left with the limit as h approaches 0 of 2xh plus h squared plus h all over h. And now if we try to evaluate this limit, what do we get? Plug in 0 for h, what do you get?
0 over 0.
0 over 0. So let's factor out the h and cancel, and we don't need to really write out the factoring of the h. We can just divide each of these by an h. So that gives us the limit as h approaches 0 of 2x plus h plus 1. Everybody agree with that?
Yeah.
All right, and as h approaches 0, what do we get? 2x is still just 2x. H becomes 0, and 1 is still just 1. And so this is telling me that the slope of x squared plus x is always equal to 2x plus 1. So if I want to know what it is specifically at x equals 0, and that's what this vertical bar means. It means we're going to evaluate this at x equals 0. What do we get? We get a slope of 2 times 0, which is 0 plus 1. So the tangent line to x squared plus x should have a slope of 1 and should go through the point 0, 0. Well, that should just be the equation, what? Y equals x, shouldn't it? Yeah, no, maybe?
Yeah.
All right, cool. So let's go in and take a look in Desmos at x squared plus x, and then here's the equation y equals x. And if we look here, this is the tangent line, right? The tangent line is y equals x. It touches the function at 0, 0, but it stays outside of it, below it all the time, right? And if we zoom in far enough at that point 0, 0, and closer we zoom in, right, it starts to look more and more like it, doesn't it? And eventually, there'll come a point where I've zoomed in far enough where they're just completely overlapping each other and we can't tell any difference, right? And so right at that point, at x equals 0, we know the slope is equal to 1. Good or no? Any
Good.
questions? Any questions on that?
So we did get 2x plus 1. So how does that relate to the final tangent line of y equals x?
Okay, so we got we got 2x plus 1, and this all the way down through here, this 2x plus 1, this is the derivative. And what we did was we were looking for the tangent line at x equals 0, so we evaluated it 0 to get a slope of 1. And that's where this came from, right? Y, if we were to write it in point slope form, y minus 0 equals m1 times x minus 0. And that's where we got the y equals x from. We're going to do it with another point right now with the same function also. So hopefully that'll help clear it up. Does that make sense a little bit better now or no?
Yeah, I get it.
Okay. We're going to do it with another point anyway, I was planning to. So let's suppose we wanted the function was still x squared plus x, and we were interested in the point at x equals 1. So if x is 1, what's f of 1? Should be 2. So the point we're looking at is 1, 2. And we already went through all the way through here and found that the derivative, right, this limit as h approaches 0 of the difference quotient was 2x plus 1. And so we'll say at x equals 1, this becomes 2 times 1 plus 1, and we get a slope of 3 this time. Everybody okay with that? All right, we did all this work on the previous page, yeah, to get that derivative. And then we just evaluated it at a new number at x equals 1 to get 3. So our equation should be y minus 2, y minus y1, right, equals m3 times x minus x1. And point slope form's always good. You don't ever need to convert out of that unless they specifically ask you to on the AP test, and I will never specifically ask you to. So let's go in and get rid of y equals x now. We had y minus 2, right, equals 3 times x minus 1. And if we look at that, it sure looks like that's coming up. It's below our parabola. It touches that point at 1, 2 and stays below it. And that's the tangent line to the function at x equals 1. And if you zoom in enough, right around x equals 1, you can see that it begins, gotta keep 1 in the middle there. It begins to look identical. Good or no?
So when you take derivatives, it's like at specific points, right? So it would be different if you chose a different point.
So the derivative is specific to the function, right? The derivative itself is 2x plus 1 for this, right? So we went through and did all that process and got that the derivative was 2x plus 1. No matter what, for x squared plus x, the derivative is 2x plus 1. But the slope of the line that's tangent to the function at any point, or the slope of the function at any point, is dependent on the x value that you choose. So we chose x equals 0 and got a slope of 1, and that gave us the y equals x1. And then we chose x equals 1 and got a slope of 3 and made this equation, and that's the tangent line. But they all come from the same derivative. Does that make sense or no?
Yeah, that makes sense.
So like, for example, we got a couple minutes here, so I'm not gonna do a whole nother new problem. But suppose we've gone through and wanted to do this with the point at x equals -1. We're still f of x equals x squared plus x. Well, f of -1, what would that be? That'd be 0, right? So we'd have the point -1 comma 0. And the derivative wouldn't change, right? Our derivative would still be 2x plus 1. And we would evaluate it at x equals -1, which would give us a slope of -1. Y minus 0 equals -1 times x minus -1. And we would see if we tried to plug that in. -1, right? And x plus 1. And same thing, it'll just give us a line with a new slope, right? It touches that point, stays below that function, and using the same derivative.
So once you
Everybody
find
good
the
with that?
derivative, the work is like kind of easy.
Sorry, say that again?
Like once you find the derivative, all you have to do is like plug in, like the work is kind of easy from that point.
Yep, I mean, just finding the point and doing point slope form. If it asks you, this one was asking us to find the equations of the tangent lines. Yeah, I'm going to ask you to do other things also. But yeah, the work is, that simple, finding the derivative and then plugging it in. It's a little bit of a pain to find the derivative, right? But it could be worse. It's going to get a lot worse for some more complicated functions. But the good news is we're going to also use this difference quotient. Once we finish up with this stuff on Thursday, we're going to use the difference quotient to prove some rules to make our derivatives much easier to find. Right, this one, not too bad. A little bit of algebra, maybe a chance to make a mistake or two in there. But when I start giving you ones like, what is that one? 1 over x, or x squared plus 1 over x, or square root of x, those ones are going to become a little bit more of a pain to find that difference quotient. So we're gonna do a few of those, and then we're gonna apply some generic rules to make life easier. Any other questions on that today?
Like just curious, like the derivative of like a linear function would be just the same thing as its slope, right?
That's correct. Yep. So the derivative of y equals x, its slope is 1, so it's just 1. And anywhere along that line, the slope should be 1. Yep. And yeah, we'll prove that. But I think that one's a pretty intuitive one to see. But also things like if you have y equals 5, like a horizontal line. Real quick, we know what that looks like. Obviously, I'll put in, let's say y equals 2, and it's a horizontal line. Well, what's the slope of this function at any point?
Just 2.
The slope is not 2. The value of the function is 2, but the slope is
0.
0. So the derivative of this number 2 is 0. Okay. Which we should, we'll be able to prove that. I mean, it's an easy enough proof. But for any horizontal line, right, slope is always 0, right? It doesn't matter positive, negative, right? The slope of that is always 0, so its derivative is always 0 at any x value. Any other questions?
So the 2x plus 1 is also, or could be also called the instantaneous rate of change for that function?
Yeah, I mean, we'll normally refer to it as the derivative. And then if I ask you like, oh, what's the instantaneous rate of change? I'll usually say like at some point, what's the instantaneous rate of change?
And that would be the slope at that point.
And that would just be the slope at that point. So you just plug in, if I said at 5, you just plug in 5 and say, oh, it's 11 there.
Okay.
Yep. Cool.